Hello, I'm Devadiga. Let's take a look at my journey throughout the autonomous robotics course at the University of Maryland. The main objective of the course was building an autonomous robot, focusing on its software and hardware aspects that would eventually compete in a grand challenge. The first step was setting up the Raspberry Pi 4 Model B, which is essentially the brain of the robot, by installing the OS and the required Python libraries. The next step is building the robot from ground up. Let's take a look at how that was done. In order to achieve autonomy and complete the grand challenge task, all the following modules needed to be designed and programmed. And these were modularly addressed through the assignments completed during the semester. Let's take a look at them. This is the final challenge setup. The robot starts from the starting zone and then has to autonomously detect the red, green, and blue block and individually place them in the landing area. It has to complete this run without knocking the dummy blocks and keeping a safe distance from the arena walls. Here, from the robot's perspective, you can observe the arena surroundings. The camera captures an image of the arena, and a color masking technique based on HSV is applied to iteratively detect a red, green, and a blue block. Once the robot identifies a block, it generates a bounding box around the corner of the block. To align itself with the block, the robot calculates the offset value by determining the difference between the center of the image and the center of the block's contours. Using feedback from IMU, the robot then adjusts its orientation accordingly. After successful alignment, the robot calculates the distance to the block by analyzing the contour's width. It then moves the calculated distance using feedback from the encoders. The next step involves gripping the block using repair mechanism and then utilizing IMU and sonar sensors, navigating along the wall, moving towards the designated landing zone, and successfully placing it. In the case that the robot is unable to detect any block in the surrounding, it tries to move towards right, looking for any block in the side, and completes a 360-degree rotation until it finds a block that it needs. This is a video of a practice run that was completed one day before the grand challenge, where the robot successfully detects one red, green, and blue block and places it in landing zone. It is the trajectory of the bot during the practice run. The zigzag patterns are the movements of the robot aligning itself to the block. Unfortunately, despite successfully detecting and navigating towards each red block in the arena, my robot failed to place any block in the landing zone. This issue arose due to improper contour detection. As you can observe from the displayed images, the robot only detected a portion of the block due to uneven robot lighting condition. Consequently, when the robot moved closer to the block, it overshot the required distance, leading to accidentally knocking it off and then dragging it towards the landing zone. To prevent such occurrences in the future, I plan to implement the following improvements. Firstly, I would generate a broader range of HSV values to ensure the detection of the entire spectrum of red, thereby increasing the accuracy of the contour identification. Additionally, I would concatenate the detected contours to obtain a more comprehensive representation of the blocks. Furthermore, I will fine-tune the configuration values in the actual arena setting to mitigate any anomalous behavior and account for the variation in the lighting conditions and other potential factors that may affect the conditions of the robot. Discussing the challenges encountered in this course, there were numerous hurdles to overcome. As someone with a software background, this project marked my first intensive venture into hardware, which I tackled independently. While locating bugs in code is relatively straightforward, pinpointing the precise point of failure in hardware project comprising multiple components proved to be a daunting task. Another challenge involved the overall design and placement of the sensor, which I found myself modifying continuously over the course of past 6 months. This adaptability was necessary to accommodate various scenarios I encountered along the way. Additionally, fine-tuning the HSV marks, the motor PWM settings for different lighting conditions, and addressing the friction between different types of flooring posed a substantial challenge that needed to be resolved before commencing the actual task. Furthermore, handling errors, garbage values, and unchanged data from the sensor proved to be an interesting task requiring careful consideration and problem solving. Despite these challenges, this project proved an exceptional learning opportunity and I thoroughly enjoyed the process. I expanded my knowledge base significantly and it allowed me to have a great deal of fun along the way.